We are moving on to our second keynote of the day from Professor Dana Kulić of Monash University on learning from human-robot interaction. A few words about Professor Kulić. Professor Kulić conducts research in robotics and human-robot interaction and develops autonomous systems that can operate in concert with humans, using natural and intuitive interaction strategies while learning from user feedback to improve and individualize operations over long-term usage. Dr. Kulić received a combined BSc and ME degree in electro-mechanical engineering and a PhD degree in mechanical engineering from the University of British Columbia, Canada in 1998 and 2005, respectively. From 2006 to 2009, Professor Kulić was a JSPS Post-doctoral Fellow and a project assistant professor at Professor Nakamura-Yamane's laboratory at University of Tokyo in Japan. In 2009, Dr. Kulić established the Adaptive Systems Laboratory in the University of Waterloo, Canada, conducting research in human-robot interaction, human motion analysis for rehabilitation, and humanoid robotics. Since 2019, Dr. Kulić is a professor and director of the Monash Robotics at Monash University, Australia. In 2020, Dr. Kulić was awarded the ARC Future Fellowship. Her research interests include robot learning and human-robot interaction. And with that, without much ado, let me introduce Dr. Kulić to you. She's joining us from Monash for her second keynote speech of the day. Thank you.
Hello, can you hear me?
Yeah, you're good.
Perfect. Let me just share my screen. Okay, can you see my screen?
Yes.
Perfect, thank you. Good afternoon, everyone. And thank you, Tirtha, for the kind introduction, and to both Tirtha and Paolo for organizing the ACRA conference, especially during these challenging times, and for inviting me to give this presentation. So as Tirtha mentioned, my research area is in human-robot interaction. As we all know, in recent years, we have seen an explosion of research in machine and specifically deep learning, and these fundamental advances have had a huge influence in many domains. And learning is now also breaking through in human-robot interaction. So in this talk, I hope to tell you a little bit about how we are taking advantage of these recent advances for learning in HRI, but also about some aspects of HRI that are unique and still pose unsolved problems. So the first challenge of HRI is expectations. For most of us, well before we encountered a real robot, we became aware of robots through movies, books, cartoons, and other forms of fiction. And the robots of our imagination are not just capable of performing a variety of tasks, they can anticipate our wishes and cater to our every need. So when people encounter robots in real life, they have some pretty high expectations of what robots will be able to do. Unfortunately, real robots are still very far from achieving these capabilities. So why is this? Part of the problem is that our techniques for developing robot behaviors come from our robotics industrial background, where robots operate in very carefully controlled environments where every action can be pre-programmed. However, humans operate in very dynamic environments and are themselves not always predictable. So to achieve the level of performance that many people expect, robots need to become much more adaptable and agile. They need to learn about the environments that they're operating in, and specifically, they need to learn about the preferences and the needs of the users. So I want to start by analyzing the HRI context so that we can better understand what exactly is it the robot needs to be learned. So one thing to realize is that HRI is actually very broad, and there are many possible configurations. So one way of thinking about the possible kind of taxonomy of HRI is to think about what are the roles of the human and the robot. So one possible configuration is that we have a human teacher and a robot learner. So in this kind of role assignment, the human knows what they want the robot to do, but needs to impart this knowledge to the robot. So a good example is a robot that is being introduced into a user's home. So the robot might already come with some pre-existing skills, so it knows how to pick things up, it knows how to put things away, but it doesn't know what the user's preferences are. So there are certain things that the user wants the robot to do in a specific way. There are certain times when the robot should be active and not, and so on. So what the teacher is trying to tell the robot is kind of what to do and what are the person's preferences about how to do it. Now, in this particular example, the human and the robot are co-located, but we could also have a situation where we have a human teacher and a robot learner, where the robot and the human are in different environments and are maybe communicating asynchronously. So a good example would be a robot that is on Mars and a human operator that's trying to tell the robot what to do, from Earth or from orbit. Now, depending on the type of role assignment that we have, this also implies different learning tasks. So in this case, in the case that we have a human teacher and a robot learner, what's implied is that the robot knows how to perform actions, but needs to learn what the objective is. Now, a second type of role assignment might be that we have a robot teacher and a human learner. So a good example of this is rehabilitation. So in this case, the robot knows what the target motion profile is, and that's, for example, been specified by the physiotherapist. But the question is, how does it help the patient to get to that motion profile most efficiently? So thinking about what the learning task is here, the robot knows the objective, but it doesn't know how to achieve that objective. So basically what it's trying to learn is the policy. A third type of role assignment is where we have human-robot peers. So here there isn't kind of a teacher-learner interaction, but both team members are kind of on equal footing, and they may have complementary capabilities, and they are working together to accomplish a shared task. So a good example of that is the picture that I'm sharing here, which is something like collaborative load carrying. And again, with this kind of role assignment, we could be co-located, such as the example of cooperative load carrying, or it could also be an asynchronous or remote collaboration. So depending on the type of role, we can see that we have different learning tasks, and that also implies that we would use different learning approaches. So for example, if we're trying to figure out what's the robot's objective, this kind of maps to inverse reinforcement learning. If we know the objective, but what we're trying to do is learn the policy, this maps to reinforcement learning. Now, the other important question when we're trying to set up the learning problem is kind of what can we assume about the environment that the robot is operating in, and particularly what can we assume about the human partner. So if we can assume that we have a good model of the person, of how the person is likely to act during the interaction, we can use model-based approaches. If we think that most people in this scenario are likely to respond in the same way, so we think that shared commonalities in human response are important, then we can think about big data approaches where we collect large data sets of how people typically respond in this scenario, and then we can use knowledge from those large data sets to generalize to a new user. On the other hand, we may have a context where we think that actually each person is likely to respond differently, and maybe even for the same person, their response is likely to change over time, in which case we have the scenario where individual characteristics dominate. And in this case, we may prefer to use online learning approaches. So here we have mapped from the context to learning approaches. And so maybe, given the recent advances that we have seen in machine learning, our problem is essentially solved. Now that we've identified what learning approach we need, we can just go to our, deep learning, toolbox and select the appropriate methodology. And it's definitely true that in the last few years, as we all know, machine learning has been making amazing progress. And here I'm highlighting the result from a few years ago when the system that was developed by Google was able to beat the top human player at the game of Go. And this was an amazing achievement. However, there are a few things that these amazing results rely on that we need to kind of carefully examine for the context of HRI. So the first thing is, this type of system commonly relies on the ability to learn in simulation. And that implies that we have a simulator that is a good model of reality. Typically, these kinds of systems also rely on the ability to learn from errors. So the system simulates its policy through many, many different trials. And then if it makes a mistake and loses the game, it simply moves on to the next game. And this implies that errors are cost-free or very cheap. And then also with these kinds of systems, here I'm showing a figure from this paper. It shows the learning, how long it took to train this system. And we can see that the time scale is on the order of days. So these kinds of systems typically require millions of experiments, which implies that the time and cost of experiments is low. And these assumptions may not be appropriate for human-robot interaction, especially if we are going to be learning anything online during interaction. Adaptation needs to be much faster than on the order of days. And we also may not have a good simulation model of the task or of the likely human response. And finally, most critically, errors might be very costly. And so we need to think about how we can, take advantage of these fantastic advancements in machine learning, but in a way that is appropriate for the human-robot interaction context. So in this talk, what I'd like to do is kind of highlight 3 case studies of recent work in my group that looks at some of these issues. And I'm going to divide this based on kind of the role assignments that we just talked about. So everything that I'm going to be talking about today is very recent work. Everything is work that has been done since March this year. And as you can imagine, our work and ability to conduct experiments this year has been significantly impacted by COVID-19, especially since most of my team is based in Melbourne. And so part of this talk will also be a little study on how to do HRI research during worldwide lockdown. Okay, so let's get started. So the first case study that I want to cover is when we have the scenario of a human teacher and a robot learner. So what we would like to do is estimate human objectives from observed demonstrations, observed actions of the human teacher. So this role setting of human teacher robot learner is a very common one in the HRI literature. Essentially, what we're trying to do is to learn from human demonstrations. So this is known learning from demonstration or learning by imitation, and it's been a very active research area for the last 15 years. And there are 2 common approaches. One approach is to learn the policy directly. So we observe the demonstrator's trajectories, and then we kind of come up with some kind of model of those trajectories, and then we try to reproduce that on a robot. Another type of approach is to learn the demonstrator's objective from the demonstration by learning the cost or reward. And this class of approaches is known as inverse optimal control or inverse reinforcement learning. So the hypothesis here is that rather than learning the trajectory, what we want to learn is some kind of more abstract representation of the human's objectives in the form of this reward or cost function, and that this representation will be more easily generalizable, both for the case when the human demonstrator and the robot imitator do not have the same physical morphology, and also for the case when the robot needs to adapt to a slightly different scenario than what the demonstrator showed in his or her demonstration. So one example of this approach that I want to highlight, this is the work of my PhD student, Vlad Zhukov, who is still based in Waterloo. So here is an example. So we have a data set that was collected by Kansari and Billard, the LASA handwriting data set. And here the objective is to figure out a high-level model for each letter, and then use that model within an MPC framework to kind of copy the writing on by the Panda robot. And I'm kind of highlighting this work because this work was done by Vlad while in lockdown. So in this case, we actually had to arrange to get the panda from the lab into to Vlad's home, and he was able to recreate the lab setup at home and conduct these experiments. Okay, now most of these existing approaches assume that the demonstration is perfect. So that implies that the demonstrator is an expert. And in the work that I want to tell you about in a bit more detail today, we wanted to understand what happens if the demonstrator's expertise is variable and we don't know the level of expertise a priori. And this is the work of my research fellow, Pamela Carreno-Medrano, and also a collaboration with Steve Smith at the University of Waterloo. So to give you an example of where this kind of expertise question might come in, consider the case of integrating a mobile robot into a warehouse. And this case scenario was actually introduced to us by an industrial partner, ClearPath, while Pamela and me were still at the University of Waterloo. So in this scenario, the robot is to be introduced into a warehouse space that is already being used by human users, so workers who are on foot, and also human-driven vehicles such as forklifts. And so to introduce mobile robots that can operate in this kind of shared space, the human teacher needs to let the robot know about what the expectations for robot behavior are in this space. So the robot would be given a map of the environment. And here I'm showing an example of a real warehouse map that we got from our industrial partner. So to deploy an autonomous material transport robot in such an environment, the robot is first given the map of the environment. And then the human operator specifies on the map kind of where the robot should go to pick up material and drop it off, but also specifies things like where the robot should avoid going, if there are any no-go or avoidance zones, if there are any zones of reduced speed. And also, existing vehicles in this environment are already respecting road rules. So things like roads, one-way roads, and so on. And so these also need to be specified by the operator. So these constraints might have more or less importance, and this is what the robot doesn't know. So the robot then can observe human drivers traversing the environment, and this can be either by observing the human-operated forklifts or by having an operator teleoperate the robot. And so from these observed trajectories, we want to determine both the relative importance of the constraints as well as the expertise of the demonstrator. And this expertise question is especially salient if we're talking about teleoperation, because we might have an operator that is extremely knowledgeable about the warehouse environment, but who doesn't know about exactly kind of what are the capabilities and limitations of the robot, and may not have great facility with the teleoperation interface. So we might get some demonstrations that don't exactly capture the operator's preferences because of their lack of familiarity with the robot and the interface. So what we would like to recover from the demonstrations, both an estimate of the expertise and also the true preferences of the user. So how do we approach this? So we model the system as a markup decision process. We know the dynamics of the robot, but we don't know what the reward is. And so what we would like to actually estimate from the demonstrations is the reward. So we model the reward as a weighted sum of known features. And these features include how fast the operator wants to get to the goal, as well as how much the operator cares about avoiding no-go zones, respecting road rules, and all the other constraints that they've specified. We then also model the user to be acting according to a maximum entropy policy. So this policy is basically saying that the user is trading off between maximizing the reward and maximizing entropy. And this trade-off is governed by this parameter beta. So if beta approaches 0, that kind of user is only maximizing the reward, and that corresponds to our expert user. Whereas if beta approaches infinity, basically that user is maximizing entropy and performing random action selection. So that's basically a complete novice. So what we would like to do is simultaneously estimate the reward which is captured by the parameters of the reward function theta, and the user's expertise, which is captured by this parameter beta. So we propose to do this with a Bayesian approach. Basically, we observe some human actions or human trajectories, and we want to apply Bayes' rule to figure out what is the likelihood of the reward parameters and the expertise parameters given the observations that we have seen. And so what we would like to do is maximize this posterior. And we have, so basically we're applying Bayes' rule. We have some prior about what we think the reward might be and the user's expertise might be. And if we don't know, we might use a uniform prior. And we want to figure out what the reward and the user expertise is after observing the demonstrations. So we can do this using discrete set inference, where we discretize the expertise and the reward weight space and define a fixed set of hypotheses. And then we update the belief over these over the hypothesis set after observing the demonstrations. Or we can also do this in the continuous domain by basically maximizing the posterior. And we might also include some regularization to that optimization, for example, by preferring a sparse reward function. Okay, so to evaluate this approach, we first did this in simulation. So to test in simulation, we first randomly generated a number of different environments with different zones. And here I'm showing some images of kind of some sample environments. So the red areas indicate areas to be avoided. The blue areas indicate roads, so specific traversal directions. The yellow areas are slowdown areas. Purple areas are high traffic, and then static obstacles are black. And then we also randomly generate a goal location within that environment, which is indicated by the green circle. Then we generate random user models using our user model. So we have users with different reward functions and also different expertise levels. Now, once we are given, we have a user and an environment, we can then generate example trajectories from this user. And then we use those trajectories as input into our algorithm. We then try to recover the user's expertise and underlying cost function based on these trajectories. So one advantage of doing this in simulation is because for the simulated users, we know exactly what the true reward was and what the true expertise was. So then when we generate the estimate, we can kind of compare the two. Now, one question about how to evaluate the reward. We know that we can only recover the reward up to scale. So we can compare the weights using cosine distance. But there's another potential issue, because for the demonstrations we have observed, there might be two different reward functions that are both maximized by the same set of trajectories. And so if we compare in the weight space, it will look like they're different, but actually, if we both of those two reward configurations lead to the same behavior. And so to capture this possibility, we can also evaluate based on regret. And so regret tells us how much reward did I sacrifice by optimizing cost function A versus cost function B. So let me show you a couple of results. So the first thing that we want to evaluate is, okay, does actually estimating both the expertise and the reward help? Because most existing approaches actually just assume that we know the expertise of the user and only estimate the reward. And so what we can see from these results, so the top set of results show the regret metric and the bottom show the cosine similarity. And the green results are for the full estimate, so estimating both the reward and the expertise at the same time. And the orange results, we fix beta, so we assume that we know beta. And what you can see here is that the results are far worse when we assume that we know beta, particularly when we have a low expertise user, which we would have expected. Now, the next thing that we are very interested in is how fast can we generate this estimate? So here I'm showing the regret, the cosine similarity, and the distance between the predicted and true expertise as a function of the number of episodes. And so we can see here that basically after observing between 5 and 10 trajectories, we can already get a fairly good performance, but the performance is worse for especially for estimating expertise for low expertise users. Now this all looks great in simulation, but what about applying it with user data? So in this case, we took advantage of an existing user set. So we had previously collected a user specification data set where we gave users a sample environment that I'm showing here. And we asked the users to provide a specification to specify roads, no-go zones, and so on. And then once they had provided that specifications, we asked them to teleoperate the robot to kind of demonstrate how they would wish the robot to behave according to that specification. Now, in this case, we only had one demonstration trajectory, so a very low number of demonstrations. So we actually applied our Bayesian framework not after each trajectory, but actually after each action. So let me show you some sample results. So on the left, what I'm showing here is the participant's specification, where the red indicates no-go zones, the green indicates road specifications, and then blue is the user's demonstration trajectory. And on the right, I'm showing the same participant specification and the path that is generated using the recovered cost function. So in this case, the system estimated that this was a high expertise user. They still had some small deviations from the target trajectory. And you can see kind of this is their demonstration on the left, and this is what the system estimated would have been the optimal demonstration on the right. Now here is an example of a novice user. So again, on the left, I'm showing their specification and their demonstration. And then on the right, I'm showing what the recovered recovered optimal demonstration is. So you can see here, we see with this demonstration, there's a lot more kind of jitteriness. The person's vehicle was kind of drifting a bit. And for these reasons, the user was estimated to be a low expert user. So to summarize, one of the key findings of this study is that if we assume that we have an expert demonstrator, this can lead to incorrect reward recovery, especially if the demonstrator is not an expert. So it's very important when learning from a demonstration to take the expertise level into account. So our proposed approach can generate accurate estimates within a few demonstrations. However, it is harder to estimate novices. Okay, now I'd like to move on to our second case study. So in this study, I want to consider the role assignment where we have a robot teacher and a human learner. And here what we want to do is we want to estimate the best policy to guide the user to some target. And of course, this is a very common challenge in robot-assisted rehabilitation. And in this project, particularly, we were focusing on gait therapy for Parkinson's disease. So Parkinson's disease is a progressive neurological disorder that results in motor disturbances. A very common symptom includes freezing of gait. So what happens during freezing of gait is people who are suffering from Parkinson's disease have trouble initiating gait, and then they also have trouble. So it's kind of preceded by kind of a shaking motion, and then they either cannot initiate gait, or when they initiate gait, the steps that they take are very short, too short. However, it turns out that this symptom can be alleviated quite effectively by providing cues on when to step. And 3 different types of cues have been investigated and shown to be effective. And that's being shown in the illustration on the right. So one type of cue is visual stimuli, where basically visual targets are either projected or taped on the ground, showing the person where to step, so providing a spatial cue. Another type of stimulus is an auditory stimulus. So this is something like a metronome or beat. And this provides the user with information on when to step. And the third type of stimulus is tactile, where the person is tapped either on the leg or on the foot. And this tapping provides, again, a temporal stimulus on when to step that is very helpful to allow patients to overcome freezing of gait. Now, most existing approaches generate a fixed on-demand cueing strategy. So what that means is that there's most of these algorithms kind of have a two-step approach. The first step is to detect that freezing of gait is occurring. And then the second step is to provide the cue. But once the cue is provided, the cue is fixed. So there might be some pre-use adaptation. So for example, based on, if we're talking about visual cues, based on the person's height, the step size will be configured. Or if we're talking about auditory or haptic cues, some user-preferred frequency will be specified. But that's all done prior to deployment. And then once the person is using the system, there is no further adaptation. However, this kind of fixed cue provision strategy may not be effective because users might have their response to cues might change over time as a function of their medication and other, the development of the disease and other factors. So we wanted to develop an approach for online optimization for cueing, and this was inspired by works that on human-in-the-loop optimization for gait rehab that had been applied to exoskeletons, but they had never been applied to this kind of Parkinson's disease context. So here's an overview of our proposed approach. We have a user, and what we would like to do is measure their gait. So in this case, we're using inertial measurement units, so gyroscope and accelerometer attached to the user's leg. So from that IMU measurement, we want to model a human gait. Particularly, we want to figure out what is the person's current cadence. And then we want to provide the user with a cue. And so we're kind of working towards a general framework where we could use either auditory or tactile cues. But in this first study, we focused on audio cues. So we're essentially providing a beat. But instead of providing a fixed beat, what we would like to do is we would like to learn a model of how the cue influences human gait. And then we want to use that model to optimize the cue selection. And we want to do this because we think that people's response to cues is likely to be individualized and changing with time. We want to do this entire thing in kind of an online manner. So here's our approach. So for the gait model, in this first study, we're going to assume that we have periodic gait. And so we model the gait signal as a weighted sum of sinusoids. And what we would like to do is learn the model parameters online using incremental updates from IMU signal data. And here we adapt the approach from Petrich and colleagues that has been validated to work on gait data from elderly adults. Those results are the results are being shown in the images on the right. So what you can see in the top panel is the gyro signal estimate, and the green is the estimate from the gait model. And in the bottom panel, you can see the true frequency is in orange, and the estimated frequency is in the blue, and then the estimated phase in the green. And so what this shows is that within 5 to 10 strikes, heel strikes, we converge to a correct model of the gait. Then we want to learn this model of cue influence on gait, and we use Gaussian processes to learn this mapping between the input cue frequency and the resulting person's cadence. And then we want to select the next cue using optimization. So we basically use our GP model to generate a cue that minimizes the difference between the target and the predicted cadence predicted by the GP model. Okay, so we would like to do this entire thing online, and we start from knowing nothing. So of course, we're using a gradient-based optimization that require a gradient. So when we first start learning, we don't have any information. And so basically what we do is we just start by selecting random points. And as soon as we have sufficient points to be able to estimate the gradient, then we can start selecting points based on that gradient. And so that results in a kind of two-phase behavior. We have the first phase where we're exploring, where the person is getting kind of signals that are up and down. And then the second phase, which is the convergence phase. And what you can see here is that this is showing an example experiment where we can see that basically with this exploration phase takes between 60 and 70 seconds. And after that exploration phase, we have a good estimate of the gradient, and then we can go into the converged phase. So we tested this approach with experiments with 25 healthy participants. So this was an experiment that we conducted at the very start of our second lockdown. So we spent quite a bit of time devising a methodology that allowed participants to basically perform this experiment pretty much alone. So the participants would themselves put on the IMU. They would themselves complete all of the questionnaires on their own device, so that we could have a COVID-safe experiment. So with each participant, we asked them to perform gait in 7 experimental conditions. So in the first condition, they were just asked to walk at their natural pace. There was no cue provided. And we used this first 7 minutes to measure their baseline, their basically preferred gait frequency. And then in the next 6 experimental conditions, what we tried to do is we tried to increase their natural speed up by 20%, or decrease their natural speed down by 20%. And we tried to do this for up and down in 3 different ways. So the first way was using a fixed cue. This is basically the current approach with most existing queuing systems. The second approach was to use a proportional cue. And the third approach is to use the adaptive cue using the methodology that I've just described. And we randomized the order of these conditions. And then following each condition, we asked the participants to fill out a brief survey to tell us what their perception was of the experiment. So I'll just show you a couple of quick results. So on the left here, I'm showing the mean absolute error. So the difference between the target cadence and the actual cadence. And what we can see here is that, so the A condition is the fixed, C is the proportional, and then E is the adaptive. And this is either in the exploration phase or in the converged phase. And I'm showing the results separately for when we tried to increase the person's speed, that's the up condition. And when we try to decrease the person's speed, that's the down condition. And what we can see here is that using our proposed approach, the target MAE is lowest, which is, so the error is lowest in the adaptive setting after it's converged for both up and down. Now, the other thing that's quite interesting to see is that we also looked at percent on. So what was the percentage of time that the cue was on? And what we can see here is there's a high variability in most of the results. And that is because the person's response to cues is actually highly individualized. So there were some participants that are very responsive and that are able to kind of with only very few cues, able to keep the target cadence, and others who require a lot of cueing. So it kind of demonstrates the need for an individualized approach. So to summarize, this is still very preliminary work, but it's promising to see that the adaptive approach has the highest, while having the highest error during exploration, has the lowest error after convergence. And the other thing that we noticed is that the cues generated differ depending on the participant's response pattern and ability to keep the beat. And so it really argues for this kind of individualized approach, even though these were all healthy participants. We also saw that from the user surveys, there was a very high cognitive load with the adaptive strategies. And so this is something that initially we thought was an issue, but actually talking to our clinical collaborators, they actually told us that this actually might be a benefit because having a higher cognitive demand might actually help bring attention to the task and help with habituation. And of course, this is a promising initial results with healthy participants. And what we're hoping for is that eventually, once COVID restrictions are relaxed, that we will be able to test this also with Parkinson's patients. Okay, so the third case study that I want to talk about is the case when we have human-robot peers, and especially when the human and the robot may have complementary capabilities. And the case study that I want to focus on is drone co-piloting. This kind of scenario is very common when we have collaborative task execution. So we have human and robot team members who are jointly executing the same task, but they may have different knowledge and capabilities. And this work is led by my PhD student, Cal Backman, in collaboration with Huam Chung. We were particularly interested in drone landings for this work because drone piloting is a very cognitively demanding task, and it's a difficult skill to learn. It requires quite a lot of training. And why is it so difficult? Because the pilot needs to be able to integrate perception, particularly depth perception, dynamic model learning. So the pilot needs to understand how the quadcopter responds to torque inputs. And also they need to have manual dexterity in operating the teleoperation interface. There are many scenarios where we have a human pilot, like a novice human pilot, who knows exactly what they want the drone to do. So for example, they know where they want the drone to land, but they don't know how to command the drone to do so. And so what we wanted to do is to develop a shared autonomy framework that basically provides assistance to novel pilots during landing. So we have this kind of complementary expertise. So the human pilot knows where to land, while the assistive system can provide assistance to help the pilot with the kind of the logistics and details of landing. So our proposed approach diagram is shown here. So what we would like to do here is a kind of shared autonomy framework. So first, we want to, so we have a drone that is operating in an environment and observing that environment with a camera. So we first want to learn a low-dimensional representation of the scene as observed by the drone. And we learn that using an encoder. So what we want that encoder to learn is kind of a depth map and also the location of likely landing positions. And then we want to learn a policy of what action to take given what the drone is currently observing in the abstracted scene, the dynamics, the user actions, and the previous actions of the assistants. And then what we want to do is to have this shared autonomy system where the input from the assistant and the input from the user are combined and then specified as the target velocity to the flight controller on the drone. So the first step is we want to learn an abstraction of the scene. So the reason why we want to do this, to learn this abstraction first, is that it has been shown in previous work that a low-dimensional representation of the scene can help to speed up policy learning. And so here we adapt an existing approach based on a cross-modal variational autoencoder. So the input to this network is the camera image, and then we want to recover the depth map and the relative pose of the closest landing pad as the output. Then we want to learn the policy. So here we use TD3 reinforcement learning. And our reward is the distance between the landing location and the center of the goal platform. And we perform the training entirely in simulation using a simulator called AirSim. And we use, similar to the first case study, we use a parameterized model of the user. So we basically hypothesize that the user population can be characterized by two parameters. One is the skill level, and the other is the agreeableness. So basically, how agreeable is the user to the assistance provided by the agent. And then to implement the shared autonomy, we simply average the user command and the agent input, and we ignore small outputs of the agent. So we first test this in simulation, where we modify this beta parameter of the user. The beta indicates the expertise. Beta value of 0 indicates low expertise, and a beta value of 1 indicates high expertise. And what we can see in simulation is kind of exactly what we hope for. Is we see that when we have a low expertise user and they're unassisted, they perform very poorly. But if we assist them, they can perform very well. And as the expertise of the user increases, if they're unassisted, their performance increases. But here we're showing that actually the expertise doesn't matter when they're assisted. Basically, both novices and experts perform equally as well. Of course, that's really nice, but it's only in simulation. So we next conducted experiments in a user study. So here we devised a way to do this purely online. So we had an online study where users piloted a drone in an online simulator, all using the same environment. So we had 33 participants, and each participant was asked to perform 16 landings, both first either assisted or unassisted. And the landing locations and the order of whether assisted or unassisted was selected at random. And then following each condition, we asked them to tell us about whether they had any previous experience, as well as their perceptions on the usability. So what we saw is very promising results. We saw that we could significantly increase the success rate when users were assisted, as well as reducing the error, the error at landing. And these results were significant. Now, looking more closely at the results, we see that when users are unassisted, there's this very high variance because we have users with different level of expertise. When users are assisted, the average is low, but there is this bimodal distribution. And the reason why this happens is because basically, if there are occasions when we have a novice user where the novice user has very poor depth perception, and therefore they drive the drone between two adjacent platforms, which is indicated in picture D here. And so occasionally what the assistant will do is actually drive to the wrong platform. Now, looking at the participant landing errors, here we're showing in blue all of the data when participants were unassisted, and in green all of the assisted. And we're estimating the participant's skill level on the horizontal axis using their survey responses and average landing error. And what we can see, which is very promising here, is that we have very similar results to what we saw in the simulation. But basically, when assisted, the performance is unaffected by their expertise level. They always achieve excellent performance, whereas, of course, when unassisted, performance is much better for expert users. Now, looking also at the survey responses, we saw that participants strongly preferred using the assisted mode. They felt that the task was much easier when assisted, and that they were able to land with greater accuracy and more quickly. So to summarize, we kind of started developing this shared autonomy approach that allows novice pilots to land the drone on their desired platform. In these preliminary results, it's very promising that while assisted, novices achieved a greater proficiency without any training. And here, we were able to train this policy entirely offline using a parameterized user model. Now, of course, this is still only in simulation, and we're currently working on implementing a physical study. Some of the issues that we are addressing is how to ensure the safety of the drone if there is any conflict between the assistant and the pilot. And then also we, in our current approach, we require that the model of what the landing platform looks like is known by the system. So I want to quickly summarize kind of what some of the current work that we're engaged in is looking at how we can deploy this concurrent reward expertise estimation into an active framework, how to handle larger operational workspaces, and then, of course, moving to physical experiments. And some of the questions that I'm interested in kind of that arise from this work is thinking about these kind of what should be learned online and what can be learned offline. So I kind of gave you a couple of examples of both in this talk. And then how can we best incorporate information that we have from models, from simulations, and from existing data sets? And then the other thing that's very interesting with these kind of collaborative system is what information should be shared between the robot and the user. So I'd like to end here by thanking all of my students, collaborators, and sponsors, and thank you for your attention. And I'm happy to take any questions.
So an announcement for everyone, please drop your questions at the keynote tag at the Slack channel. So while we wait for the questions to come in, I actually had a quick question for you, Dana. Mm-hmm. So can we have the both of you? Thanks. So I had a thought when we were talking about the demarcation between demarcation between unskilled and skilled operators. And so, in my, if I understand correctly, the more consistent a behavior equates to more skilled performance, more of an expert performance. So I was wondering, have you thought about, or what's your comment on for different types of tasks? So in certain areas, when the human expertise increases, they become more creative. For example, a jazz musician would actually want to improvise a lot more, which increases the variance of the task, but not necessarily because they are unskilled, but because they are expressing their creative in that sense. So I wonder, have you looked at the creativity aspect of these repetitive tasks that humans perform that can become very boring very soon in the workspace? And that was one part. The second part was, again, as the human expert becomes, as humans become more expert in a particular task, they start doing that subconsciously, which means that they incorporate additional constraints and optimize. So they might be able to combine two tasks on the day itself. Have you looked at hidden task hierarchies and see whether those appear in those expert demonstrations, or your thoughts?
Yeah, these are super interesting questions. Thanks very much for raising them. So I think actually the questions that you raise actually kind of highlight the need to be estimating both the objectives and the expertise at the same time, because you're absolutely right. An expert might.
Hello, everyone. My name is Jong-hyuk Kim from UTS.
Yeah. Just tell it to continue. You continue. We can hear you. Yeah.
Okay. Sorry, somebody else jumped in, so I wasn't sure if.
No.
An expert might have a different way of performing the task, but they might also have different objectives. And so that's why actually the difference between an expert demonstrator and a novice demonstrator might be included both in what objectives they're optimizing, as well as in how well they're able to achieve those objectives. And so I think that actually highlights the need to not just assume, we want to estimate simultaneously the objectives and the expertise. We shouldn't just assume that everybody has the same objectives and we just need to estimate the expertise. And so I think this is actually something that our framework, can contribute to. And I absolutely agree with you, especially if we're looking at longer demonstrations. We should not assume that the objective is constant throughout that demonstration. I also want to come back to this. It's kind of a very interesting question about this question of, does the variance increase or decrease when you have an expert, particularly with creative tasks? And so what I think actually would happen is that you would have certain dimensions where the variance would decrease. So for example, a novice person, trying to play an instrument, they may not be able to keep the beat perfectly, but this is not a mistake that an expert would make. And then certain dimensions would increase. And so I think that what you want to do is to kind of model this, for each objective, what is the variance, so that you can kind of understand exactly, kind of a stochastic model of the user's objectives. And this is actually, so I showed very briefly that work from my PhD student Vlad on handwriting. Actually, one of the things that he's doing, so he's actually modeling human motion trajectories using Gaussian processes. And that's exactly the kind of thing that we can recover. And so you basically are recovering for over a set of trajectories, both kind of the mean and the variance. And so you can tell kind of which parts of the trajectory there's very low variance. So these are kind of like, if you're playing an instrument, there are certain things that you need to, if you're playing in a band, there are certain things where, in order to kind of be a good member of the ensemble, there are certain rules constraints that need to be satisfied. And then there are certain moments when you are free to to improvise, and there would be a high variance. So I think that would be possibly one approach to handling that kind of demonstration.
Thanks. Thanks for that. We have a question from Ash. The question is, have you considered using peer model to accelerate training for a novice by tuning the assistant's input progressively down until the novice can be considered an expert? And comparisons similar to evaluation approach.
Okay, so I guess the question, the first question is about, kind of do we want to, can we help the novice become an expert by kind of decreasing the assistance of the system? So I think that's a really excellent idea, and this is maybe something that would be particularly interesting for rehab. But maybe for, also I want to kind of challenge that a little bit, because maybe for certain applications, the user doesn't care about becoming an expert pilot. They just want the drone to go where they want to go. And so maybe it's better, if the objective is just task performance, maybe it's better not to try to, because there's kind of, now we have two objectives. One is to achieve the task, and the other is to improve the the piloting skills of the user. So if we're talking about something like, doing search and rescue, or, going into, maybe it's best to just focus on the task and, leave, leave the training for another time.
Thanks, Anna. So while we wait for a few more questions, I have a quick question regarding the third component where you were trying to land a drone. And one of your future work thought processes was to actually run it on real systems. So I was wondering, have you have any good intuition about what kind of environmental model needs to be added in to condition out the performance? Because if the environmental condition significantly changes, then your parameter might be quite different from what you end up training.
Yeah, so actually, I didn't kind of describe this work in detail, but actually, when we were training the system, we actually trained in the simulator with many different environments. So we kind of create, like in the simulator, you can kind of create various different environments, and we had different locations of landing pads and different textures and different scenes, and so the system was training on all of those. And then when we ran the user study, we chose one particular environment that wasn't part of the training set, but of course we had all of the users just use the same environment, just so that we would then remove the potential confound of, if one environment was inadvertently more difficult than another. So we are actually hoping, like, our first step is we're going to see if we can actually do a sim to real without, with just having these many different this kind of domain randomization over environments in simulation, whether we can kind of just use that directly. But yeah, we will. I don't know yet if that will work, so we will see. But the one I think the one weakness, which I think I mentioned in the talk, is that we do, when we are creating these environments, we, as part of the training, we tell the system, these are all the possible landing locations, right?
Mm-hmm.
So then we have some kind of model of what does a landing spot look like. And if we have a user that has a different idea, maybe we think, okay, a minimum landing pad is a certain size, but a user thinks like, I can land a drone on something much smaller than that. This would be a limitation, because then the assistant might not realize that wherever the user wants to go is actually a potential landing target.
Thanks, Dana. While we are waiting for, please continue sending some questions. That I wanted to piggyback on your previous comment was, have you so you have worked with manipulators and drones and different kinds of robots. Can you make a comment on how the complexity of the problem changes with dimensions when you're learning? Is it the same thing, or are severely constrained robots, learning from a demonstration for severely constrained robots is a different problem set altogether from high dimensions, but less constrained?
Yeah, that's a really good question. So there is kind of, I guess, pros and cons. One advantage of learning from demonstration for humanoids is that the humanoid, the system is very complex, but there is this direct mapping between the human demonstration and what the robot should be doing. Whereas if you're trying to learn, where you have a human demonstration but the robot morphology is very different, you have to figure out what's the appropriate mapping. I think in recent years, there's been this kind of really interesting work on thinking about what are appropriate task abstractions that can facilitate learning. Because we obviously know that if we have a lower dimensional state space, a state and action space, learning can be much faster. And so rather than trying to learn in the high dimensional space of the full 30 DOF or 50 DOF of a humanoid, can we learn in some much simpler space and then, just then project to the higher dimensional space? So I think, of course, the big challenge is, okay, that's a great idea, but what's the right abstraction?
Yeah.
So there is kind of an example that I showed today, which was this idea of abstracting the observations of the drone into this basically just a representation that highlights the saliency of landing pads. But that's kind of, like a specific example. I don't think that, I think this kind of a general, what's the best way to abstract is still very much an open question.
Thanks, Dana. On that open question note, lots of interesting results expected from you. So I'll thank Dana once more for this excellent talk and thought-provoking discussions. Thank you, Dana.